My name is Michael Pollock. I'm a project consultant at IES, so pleased to be here today. What I'm going to take you through over the next couple of sessions is some work I've been preparing with regards to frequently asked questions with regards to VE compliance, or compliance in general, using the virtual environment. This all really sort of started, I guess, a few months ago when we were getting in some really worrying concerns from some of our customers who were finding that it was perhaps more challenging to meet the level of compliance that they thought they should be able to achieve. Buildings that they thought should be able to either pass the building regulations or exceed them by a certain threshold, were finding that when they set up their building to a level they thought should be sufficient, they weren't quite hitting those targets. So we were able to get on board. We were able to look into why this was the case. You know, what's happening with these models that they're not achieving the targets? Is it that perhaps the targets are a little bit tougher than they'd originally thought, or are there perhaps some issues within the model? When we looked into this, we started looking at regular support queries that come into us, issues that we identified during model audits. We identified a large number of repeated issues within models that could affect the performance that the users were getting out. Now these vary in magnitude. Some of them are fairly small. Others can be much more substantial. The causes of these vary from perhaps using a lot of the defaults, which in a lot of cases are going to be set to quite, I guess, inefficient targets. And also, a lot of the time, it's down to the setup that the users embarked on. Perhaps haven't followed all of the same modelling rules in a way which can, in some cases, have a fairly profound impact on the overall result. Now, about a month ago, we published online our first FAQ document. So some of you may have already had a chance to take a look through that. And that highlights most of the key areas that I'll be talking about today. I'll presenting you why these issues are quite significant and how you can go about setting up your models in order to avoid these potential pitfalls. Okay. Now, I'm going to start off talking a little bit about what is VE compliance, and I guess some of the issues that, again, we often get, some of the misconceptions that people have when they're performing a compliance assessment. Now, I'll be referring to 3 different building types. Most of you may already be familiar with this sort of terminology, but just to clarify things. Now, what Sarah was demonstrating earlier when she was running through HVAC is what we would refer to as a real building. Now, a real building is what we set up with all of the information that we assign to describe the operation, the design, attributed to that. So that includes all the construction information, the systems information, details about how that space is going to be occupied, ventilation rates, heating, cooling set points, and so on. Now, this real building should give us a pretty true representation as to how that building should perform if it was to be built and operated as we've described it. Now, there'll always be some issues in getting all of the information, but the more accurate we can make those assumptions, the closer we're going to be to having a simulated model that reflects the true operation of that building. The next 2 models that we'll refer to are our compliance models. These are our notional buildings and our actual buildings. Now, both of these are automatically created from our real building. So typically when a user is working with the virtual environment, they'll be interested really in the design case. So they want to know, they'll be creating their thermal model to describe, to understand how they can optimize the true performance of this building. So they can give the best value to their client. The software will then create these 2 compliance models from this, the actual building and the notional building. The actual building is in a lot of ways very similar to a real building. It has the same simple systems set up. It'll have the same fabric parameters. It'll have the same glazing areas, orientations, and location. The key thing which is going to be different about this actual building is that it doesn't use the template information that you perhaps know will be used on site. Instead, it uses information from the NCM activity databases. The actual building will also omit a lot of can be fairly substantial loads, as Sarah touched on earlier. It excludes things like a lot of process loads, elevators, sort of lifts. In some cases, these process loads can be really quite substantial and have a big impact on the overall energy performance. The heating set points will be different, or could potentially be different to what you've got in reality. Your ventilation rates, again, are different. So these all stack up to make really quite a different version of the building to what you perhaps know it's going to sort of operate as. Now, this can give rise, I think, to what Sarah described earlier as, I guess, a performance sort of gap. People often take their compliance sort of model and believe that this is I guess, of a design sort of calculation to try and get an understanding as to how that building is going to perform. And that's not strictly true. Your compliance model is exactly for that. It's for demonstrating that that your particular design is meeting the current sort of building regulations. But I would always take information on the energy or the CO2 emissions from that with a little bit of pinch of salt. What's really important is understand, well, how is my building going to perform in reality? And it's important not to forget that whenever we're working with the virtual environment. As whenever we're looking to make improvements to our design, it's not solely to try and get our building to meet compliance. We also need to remember that are these the correct decisions for a real building also? Okay. Now, the third building type is our notional building. Now, in the current regulations or framework, this notional building is used to determine the target emission rate, or the TER, for a compliance assessment. Now, prior to 2010, we had a whole heap of improvement factors and stuff which were brought in. In a lot of ways, it's a lot simpler now. The notional building directly forms that sort of target emission rate. Ergo, if our building reflects the same efficiencies, the same inputs as that notional building, we should really be on quite a good steading for hitting, for meeting compliance. Now, I think that at the early stages, I think there can be a little bit of a disconnect as to exactly what the requirements are, what requirements are for a design to meet compliance. On the left-hand side, we've got our approved document of L2A here, and this describes all the different criteria that designers need to build to. Now, to give an example, they'll have criteria 2 within there, which will give minimum efficiencies for fabric. On the right-hand side, we've got the NCM calculations of methodology. Now, this really describes how the criterion 1 calculation should be performed. It describes in detail the notional building, and detail as to how these calculations should be assessed. Now, what I think is perhaps unclear with a lot of people is that a lot of the parameters that are in the notional building are significantly better than the minimum requirements set out in the standard. So perhaps in the early stage design, if a designer is building, as an example, to the fabric parameters set out in criterion 2, they're already significantly worse off than the notional building. Which means that if they're not meeting the minimum, if they're only hitting these sort of minimum sort of U values as set out in this table, they're still a mile off the notional, and therefore it's going to be much more difficult for them to achieve compliance. Okay. Now, I think it's important at the early stages of an assessment for really designers to be familiar with what are we being compared against, because using the L2A document on its own doesn't give them that information. Now, I'm fairly well versed in the NCM modelling guide. I know pretty well what parameters the notional building is going to adopt, but your typical user of the software perhaps doesn't have all this information to hand. They don't know what they should what is a good level for them to target. Now, within the software, we've got a set of navigators. That serves a couple of functions. First function is really to guide users through the process of setting up their model for compliance, making sure they're setting all their inputs. But I've got a model sort of prepared at the moment. Here we go. So this is a model I created sort of earlier, and I've got my sort of navigators on the left-hand sort of side here. So I've selected on this my Part L2A 2010 sort of DSM sort of navigator. What this enables me to do is So it takes me sort of step by step through the setup from the geometry, through setting up my location data, and so on. What I really want to show you here is a set of reports that we have towards the end of those navigators. So we've got two reports. The first one I want to show is the key model inputs sort of comparison. What this enables users to see is really from before they even run any simulations, right at the very start of the assessment, is a comparison between what they've got set up in their thermal model, what's assigned to their actual building, in comparison to what's set up in the notional building. And this goes through a range of fairly sort of key sort of sections. So I can zoom in on this a little bit. Here we go. So the first section we've got is on sort of fabric and infiltration. Now, in this stage, I've deliberately kept a lot of the default sort of values within the software in order to try and highlight if someone's just doing a very quick assessment and they perhaps leave a lot of these settings at default values, they are going to be pretty much off to, they're going to be a good bit behind how the notional building is performing. So here we can see a table which shows us our average U values for our different external sort of wall and construction elements, a comparison between the notional and the actual building. And any area where our actual building is performing poorer than the notional building will be highlighted in red as it is here. So from a very, as soon as we've got like a basic sort of thermal model, we can start saying, well, these are the parameters that our notional building is going to be achieving. And at those early stages, just saying, well, these are really the values we should be targeting. Often you find that if you get too far down the design stage and these areas become, I guess, sort of, it becomes too late, I guess, to make changes to these early stages. It becomes much more expensive to try and adapt your design to a level where it's meeting compliance, as you're having to perhaps look at much more expensive sort of strategies to offset that difference. Now, while you're certainly allowed to perform in some areas poorer than the notional building, the whole framework of comparing CO2 is designed so that design can be flexible. You can have perhaps an increased area of glazing and offset that with a more efficient sort of chiller system. But this will just highlight, well, where are those areas where there is a shortfall. So this takes us through a lot of the, I guess, a fairly sort of key areas. So it starts off with fabric and infiltration, highlighting where our U values are being outperformed. Also infiltration rates, where if the infiltration we've specified is poorer than in the notional design. We're able to look at our assigned glazing parameters to see if that's likely to be an issue with regards to overheating and excessive cooling sort of load, where we can look at the amount of the area of glazing that's assigned to each of our zones within our thermal model. We get then an understanding, so how is that glazing distributed? In my case, for example, I can see that we've got 31% of glazing on the south facade, whereas the notional building only has 19. So it gives us key indicators as to what could potentially be causing issues for us later on down the line. When we come to systems, again we'll get a breakdown of all our key efficiency attributes. So we can see the SFPs that our notional building is using versus what we've got assigned in our actual building. And again, highlighting any areas where our building is being outperformed. As I said, I've used the default values, which is fairly typical of somebody sort of embarking on an early stage sort of assessment. And as we can see, my actual building is poorer than the notional on pretty much every single front. So I'm expecting that any sort of results I get out from this is going to be a good bit of meeting compliance. But this really shows up, well, where are these areas that we can sort of focus on. A lot of the queries that we get in are with regards to lighting. I find, well, lighting is typically one of the most dominant loads within their compliance model. And it's, in some respects, doubly sort of important. Not only is it uses electricity, so it's got a high carbon emission sort of factor, but also if we've got poor lighting gains within, or high lighting gains within our model, that also contributes to our cooling load. So any savings that we can make to our lighting are going to make a fairly substantial sort of a reduction on our building energy. Okay. So what we can see here is, again, I've got this left at the default settings at the moment, where I've got watts per meter squared value, lighting power density of watts per meter squared per 100 lux value, typically of 3.75, a couple of spaces up to 5.2. When we compare that to our notional building, again we can see that's substantially sort of lower. Now these are calculated based on the lamp efficacy for the notional building. Again, this is described in the NCM modelling guide. So the notional building has this sort of luminaire efficacy fixed at sort of 55 lumens per circuit watt. So we can see that unless we start looking into addressing these sort of issues, again, we're going to be a good bit off meeting compliance. So these sort of tables become really useful just for identifying where are the shortfalls in your model and how can they be addressed. Now, once we understand what's happening within the notional building, next I want to sort of touch on the setup of the model itself. I'm going to start off with the geometry zoning. Now, one of the most sort of common issues we see through sort of model audits and tech support is where people don't sort of follow the NCM sort of zoning rules sort of correctly. Now, the zoning rules sort of require you to split up the geometry sort of your model wherever you've got different activities, wherever you've got different HVAC systems serving a space, but also based on daylight access to the perimeter. So I've taken a relatively deep plan sort of office space here. On the left-hand side, I've got a model as if it hadn't been sort of split up at all. So it's the office space is treated as one single sort of open plan space. On the right-hand side, I've got the model with the perimeter zoning sort of in place. Now, what I've tried to highlight in this sort of a luminaire sort of arrangement here is that within the notional building, dimming controls will typically be applied to any perimeter zone. Now, because we haven't split up our model on the left-hand side into sort of core zones and perimeter zones, it's treating the entire floor plate as if it was a perimeter space. Meaning that even in these deep recess spaces, the notional building is still benefiting from daylighting controls, which it wouldn't be able to feasibly do. On the right-hand side, I've shown the same sort of setup where only the perimeter zones are benefiting from dimming control. And all of our core area spaces here, those will have their luminaires on throughout the occupied hours. Okay. And that can make really quite a substantial impact on the performance. And not only on your actual building, but also on the notional building as well. Now, even in non-compliance assessments, I would always recommend following a zoning strategy similar to this anyway. When we perform a simulation, it's going to be looking at the mixed condition of any thermal zone. And you could imagine that a zone in a corner office like this, where we've perhaps got glazing on either side, is going to feel really quite different to a space which is recessed right into the core of the building. Occupants down here might have issues with draft, radiant sort of cooling effects, and so on. So it's quite likely that in a space like this we would have a heating load perhaps on the perimeter of the building, but not in the core. Where we only treat this as one single zone, we don't get that differentiation. So splitting it up like this gives us more accurate results as well. So it is important to follow this sort of zoning strategy. Now, if you haven't if you've created your model as one single zone sort of space, it's actually really very straightforward to split it up sort of in this way. So I'll just look at my ground floor. So here's the original model that I started with, sort of in this case here. So I started off by using the construction line tools. I find this is a really good way, whenever you're sort of setting up your geometry, just to mark out where you're wanting to cut. And this just allows me to set out my perimeter zones without editing the geometry sort of in any way. So I've not changed the thermal parameters sort of at all. Once I'm happy with that sort of setup, what I can do is use my partitioning tool. So I've got my single zone there. I want to generate separate new zones. And I want to split this without partitions. So it will still be effectively one large open plan space. I won't have any partitions sort of in there, but I'll have zones at each sort of step. I can follow that process round, and that just allows me to very quickly start splitting up the floor plan. As I said, we do see a lot of models of coming in where this process hasn't been done, and it is an important step to do. Okay. The second point I want to talk about with the sort of model geometry is the use of sort of ceiling void sort of zones. Now, a lot of users will include ceiling voids sort of above their zones, so they're essentially sort of treating them as a free-floating space. They won't have any activities sort of assigned to them. There'll be the temperature they're at will be determined by the zone surrounding them and the fabric properties of the constructions surrounding them. Now, here I've got two separate sorts of models here. In one case, I've specified at the ceiling voids of level that this is adjacent to this sort of meeting zone below. In the two images here, the green is sort of represented by a meeting room, which is I think about a 2.5 metre floor to ceiling height. Blue spaces offices with about a 4 metre sort of ceiling height. Now, it's perhaps a little bit subtle, but if you look at the glazing band in these two models, in this model here, where I've told the ceiling void that it's a ceiling void attributed to the meeting room below, we've actually got a larger window in that notional building. Now, this is because the NCM rules require the amount of glazing that gets assigned to the notional building to be based on either a height of 1.5 metres or 40% of the external facade area. So in this case, the external facade is really up to my sort of floor-to-floor sort of height here. So I want to ensure that the software understands this. Now, let's see. If as we can see here, in the case where I haven't set this up, the glazing is smaller in the notional building. The impact of this is that the notional building will have lower solar gain, which will mean a lower cooling load than it might otherwise have had. And it will also mean that there'll be a lower conduction losses sort of in the winter time, meaning sort of we'll have a lower heating load as well. Because this is eventually reducing the emission or the loads within our notional building, it's also going to be reducing the target emission rate, making it a little bit achieving compliance a little bit sort of more challenging. But I've got a model sort of set up here, which I can demonstrate that in. Okay, so this is the same model that I had in that presentation here. First of all, I'll show you how we can go about sort of, making sure that void space knows it's attributed to the meeting room. So I'll select my ceiling void. So I'll just do this by level just to isolate that space. So I've selected my void. I'll make sure I'm in compliance. Okay. Now if I use my room query feature within this, there we go, and I go into my building regs tab, because this is identified as an internal void or warm roof, I've got this additional option here, which allows me to specify, well, what is the associated room to this void? If this was just a normal room, this option wouldn't appear. And that's one of the reasons why perhaps a lot of users are unaware of it. This then lists any adjacent zone to this particular void space. I can tell, well, the associated space is my L00 sort of meeting room. This is the void space attributed to it. Okay. And then that means that in the notional building, it will have the correct amount of glazing sort of assigned to it. Now, that can actually have a fairly significant impact. If I look at my meeting room, so I've already run a couple of simulations. So I've selected my I've selected my two pre-run notional buildings. One again had that link assigned, the other one didn't. And I want to look at the heating and cooling loads attributed to that zone. If I bring up my annual totals, here we go. So we can see that in the model where I have correctly attributed the void to the space, and it's got ultimately I've got the correct amount of glazing. I've got let's see, a combined heating and cooling load within that zone of 2.7 megawatts. In the model where I didn't set up that link, it's down at 2.3. So we've got a fairly substantial difference in the required sort of conditioning load of that, simply because that setting wasn't made. Now, if that was indicative of the entire building, entire floor plate, that could add up to a fairly substantial difference in the required target emission rate. We could be finding that our target emission rate was substantially lower than it might otherwise have been, and thus having this in place will just make it easier to achieve it, or allow us to demonstrate an even greater improvement on the target. Okay. Now, as I mentioned, there's some limits around the rules of this sort of glazing band. It's set between either 40% of the external facade area or 1.5 metres, whichever is the lesser of the two. So there is a sort of a cut-off threshold, where you won't see any impact. If your floor-to-ceiling height is less than 3.75 metres, it's worth making sure that setting is checked. Anything above that, and you're already exceeding the 40% threshold. So setting that link will have no impact on the notional glass. As we can see here, as we jump from a room height of 3.75 up to 5 metres, the notional glazing band remains the same. Okay. One of the other issues that we regularly see entered incorrectly is the treatment of unheated spaces within a model. Now, I've got an example here of an attic type zone. Now, there's a number of different settings that the user can apply, whether it's internal void or warm roof, buffer space, heated or unoccupied space, and so on. Now, it's important that whatever assignment you make is reflected in the constructions that are assigned as well. In this case, on the left-hand side, we've got our insulation at the rafter level. So my attic space is essentially contained inside the insulation envelope of the building. Therefore, I treat it as an internal void, or in this case, of a warm roof. That then means that when the criterion 2 checks are identifying the external fabric elements and testing to make sure that the U values are achieving the minimum thresholds, it's testing the correct surface. In this case, it will be testing the assigned roof construction. In this example here, we've got an unheated roof, where the insulation's lying at the ceiling level, and we've essentially got it's outside of the insulation envelope. In this case, this unheated roof category would be the appropriate selection. We do quite often see Bruegel documents coming in where it's saying that the building fails criterion 2, but it perhaps doesn't necessarily. It is passing. It's just down to an incorrect setting which is made. The other setting for, I guess, of an unconditioned space might be for somewhere like a storeroom, where there's no heating, no cooling, no ventilation, but it's still an occupied space. In that case, it would still be treated as heated or occupied. It's not, I guess it's the term is or. It would still have lighting gains, it would still have some occupancy attributed to it, but it wouldn't have any heating or cooling, so it would be still a free-floating space. Okay. Next slide, we'll look at the assignment of shading within our building. When we're setting up our thermal model, we can describe shading objects as 3 different categories: local shades, topographical shades, or adjacent buildings. Now, I've seen a lot of cases users will set up all of the shading, whether it's trees, adjacent buildings, as local shade. This is maybe perhaps the first object on the list, or perhaps not clear as to when it would be appropriate to use the other options. What this illustration shows here is the actual and notional building with the 3 different shade components assigned. On the building here, where I've got these bristle and vertical fins, these are assigned to the thermal model as local shades. The trees in the background are set as topographical shades, and then our purple blocks here are set as adjacent buildings. Now within the notional building, whenever we're using suncast or we're using the solar tracking facilities for our actual building, we would use the same within the notional building. But we would only want to include the shading effects of topographical shades in adjacent buildings. We wouldn't want the notional building to benefit from the brise-soleil that we've got. So it strips out, when it's performing a suncast, anything described as a local shade. You can therefore have a potential issue if a user has set the adjacent buildings or trees also as local shades, as when the notional building is run, it's going to emit any shading impact that those objects have. Now, quite often what you'll see, the impact of that would, because I guess adjacent buildings are going to be low level, it's going to be blocking out solar gains when the sun's low, so typically in the winter time, meaning that the heating loads within the notional building will be a little bit reduced as they've got higher solar gains than they might otherwise have had. By the time it gets to the summer, the sun's at a high enough angle that the adjacent buildings aren't casting any shadow in the building anyway, so we're not really seeing any saving on that on the cooling side. So we can see our notional building results being improved upon simply by excluding these sort of shading effects. So it is important to ensure that the assignment that we have is correct. Now, even after these have been created, the properties of any shading objects can be modified at any time. We can do that in Model It, if I go to my sort of properties. So, if I wanted to change this into any other type of shading object, if I go into Properties, I've got the option here to edit that into any other sort of object category. So if I have made a mistake early in the project, it's something which is very easy to rectify sort of later on, and is worthwhile doing. Okay. We're going to move on to some of the construction properties that are specifically, I guess, relevant when we're looking at sort of a compliance assessment. As it's again an area which is very often overlooked by users. I'm going to start off looking at ground contact floors. Now, within our notional building, the notional building will have a U value set at the limiting value. From memory, I think it's 0.18. It might be a little bit higher than that, or the uninsulated sort of a U value, whichever is the lesser sort of the two. Now, in this case here, I've got two different models of varying size. So the first one being the sort of small office building that we were looking at, which has a footprint of 425 sort of meters squared, and a perimeter of 84 meters. Now, when we apply the EN ISO 13370 correction to this, we find that we have an uninsulated U value of 0.367. So in this particular building, the floor would need to be further insulated. It would need to have either perimeter insulation or something in place to bring it down to the minimum sort of threshold. In the supermarket model below, we've got a much greater footprint. So when we start looking at the ratio between the floor area and the perimeter, we end up with an uninsulated U value of 129. In this case, our U value is much lower than what would otherwise be applied in the notional building, and it's this value that should be applied. Now, within the construction setup within our model, the tool guides you through that setup to make it as easy as possible to ensure that these corrections are made. I'll quickly demonstrate that on the. This model will do fine. If I jump into, let's see, my Apache HVAC view. No, not Apache HVAC. Sorry, my the compliance view. And I want to open up my sort of constructions. I'll go into my ground floors. So at the moment, I've just still got my default sort of construction sort of in place. Okay. And so this is telling me here I've got an uninsulated, because I haven't set anything, it's got this sort of uninsulated value of 0.603. I want to adjust these settings. It knows it's a ground floor. Now I want to enter all the characteristics that describe the footprint of this building, but I don't need to do this manually. What I can do is go into my ground ground contact floor plans and automatically update that from the building geometry. So this goes in and interrogates the floor, it automatically identifies the floor plan and the perimeter of the area and obtains this characteristic dimension that the E and ISO 13370 calculations require. So I'll apply and exit that. So that again gets fed into here. I can also then allow for any perimeter insulation that the building may have. This again, if it's a large footprint area, it may not be required to have insulation across a full footprint. We may only want to have it just around the perimeter of that. And this allows us to specify whether it's horizontal, vertical, how thick it is, the conductivity of it, and so on. For now, I'll say sort of none. And I want it to apply this adjustment. What you'll notice when I click apply is that it will automatically insert, I guess, a correction layer into my construction here. So I click OK. So we've got this U-value sort of correction layer. So this has now automatically updated my, my construction U-value. So I've now got a U-value for this particular construction of 0.12. And my uninsulated U-value has dropped from 0.6 down to 0.249. So in this particular case, the notional building will still be sort of unaffected. But I've been able to take into account I guess a sort of ground contact reduction within my actual building as well. So I should now find that I've got less heat loss through my floor, which is going to reduce my heating load within the building. Okay. The next construction parameter that I want to sort of bring to your attention is the visible light transmittance sort of set up within our glazed constructions. I guess most of our users are typically more involved in the energy modelling side. It's typically the layer by layer information because we're getting the right U values, the solar heat gain coefficients and so on that are important. Now, these are all, I guess, used within the thermal sort of, side of the analysis. However, this visible light transmittance characteristic is used within any dimming controls that we have within the model. When we're doing compliance, it will use the algorithms set out in the IESVE technical manual for calculating how much dimming or what reduction in lighting power a space should experience. And it takes into consideration the external luminance at any moment in time, the amount of glazing a space has, whether it's glazed on just one facade or on multiple facades, and also importantly, the light transmittance characteristics for the glazing that's assigned. Now, what I often see is customers will perhaps have assigned a glass type which has a very low shading coefficient in order to minimise solar gains, but they might have left the light transmittance at the default value of 0.76. In reality, they might only be achieving maybe 50–60% of light transmittance. So having this at, I guess, too high a level is effectively going to result in too great sort of a saving on their lighting controls. So it's important to bear that in mind. Okay. Now, in an earlier example, we talked a little bit about models which have sort of ceiling voids sort of applied within them. And that works fine within like a DSM sort of a type of assessment where we can model free-floating spaces sort of accurately. Now, the notional building automatically has assigned to it notional construction information. So it will have external walls, floors, roofs, and so on assigned. But it also has notional internal constructions as well. So a notional floor, a notional internal wall. Now, if you can imagine that in our build-up, we've perhaps got our ceiling void with maybe a 500 mils of cavity sort of, within the space. In our notional building, by default, it will have these notional ceiling constructions, which include 100 mil of concrete. Now, if we've got this 100 mil of concrete assigned to our ceiling tile level, and then a further 100 mil of concrete assigned to the actual sort of floor construction, we're introducing an awful lot of extra thermal mass sort of into that notional building. Now, the impact of this can be that it can start to even out peak cooling loads sort of within the summer. Or it can benefit from perhaps sort of the cool in the night time to store that and then release that into the space. So in order to ensure that the sensible parameters are assigned to that notional building, to prevent it from having all this extra mass, what we can do is for any particular construction, for any particular internal construction, specify that we want to retain this within the notional building, so that we don't end up having these sort of doubly massive sort of floor constructions. Probably the most common scenario where I would use this would be within modelling ceiling voids, or potentially sort of raised floor plenums as well. Okay. I'll come on the sort of last section of the constructions. Then it might be a good time to take a break. Now, within compliance, there's different types of door categories that can be assigned to models. The door element itself can be a really useful facility for assigning a variety of different construction elements within our model to reflect different components. It is, however, important that we specify what type of door element that is. As you may recall from our Criterion 2 details, that things like personnel doors will have different performance attributes to vehicle access doors and so on. Now we can also use the door component for modelling things like curtain walling, where we might sort of have a curtain walling insert into sort of perhaps a traditional wall construction. And that forms quite an easy and intuitive way of having these sort of multiple opaque constructions within a single surface. Okay. Now, whenever we do that, it is important that we specify what type of door element that is. So I jump into one of my door options here. So we've got a bunch of NCM ones. I'm just going to the construction we've got here. So we do have this drop-down panel here, which allows us to specify, for this particular construction, wherever this is assigned, this should be treated as a personal door, vehicle access, but also this wall or roof element. If we did want to represent different opaque constructions within a particular surface, or also, as I mentioned earlier, potentially sort of curtain walls as well. Now, it's worth noting that with the curtain wall assignment and the 2010 sort of regulations, if you've got a building which does have a large amount of curtain walling, the notional building will replace that with a traditional wall construction, so at 0.26 watts per metre squared sort of U value. Now that was different in the 2006 sort of regulations. So if you do have a lot of this sort of a spandrel panel sort of within your design, you can find that the net sort of U value of your building is substantially higher than what's in the notional building. It's something to be aware of. And things like the tools and the reports I demonstrated earlier are very useful for highlighting that to designers at the early stages. What's also important to note is that it's wherever we've got glazed windows, as sort of highlighted sort of in here. So we've also got that door drop-down sort of menu within the glazing option. It's important to specify that it's not in fact a window that you've modelled. It's a door, and that can either be of personal or vehicle access or similar type. Okay. Now, whenever we do have a glazed door within our within our actual building, again, it's important that we set that correctly in the constructions, as it will be treated as an opaque door within the notional building. Okay. So that's just a couple of screenshots of the same building with the actual and notional, where it's automatically replaced the glazed door with the notional sort of opaque door.